All right, so we have one question left in 2.8, and in 2.8 we had talked about a couple of theorems. One was Raleigh's theorem, and the basic idea of Raleigh's theorem is it told you when you can expect to find a tangent line that's horizontal. That's one of the things that Raleigh's theorem did. And then the mean value theorem talked about when you will be having a tangent line that has a certain kind of a slope that would match another slope that you'd already found. And then what we were taking a look at in the last question was an extension of that idea, talking about when functions are increasing, decreasing, or neither. Now we've talked about these ideas, but we've never sort of written them down formally, that we've looked at them in this way, and this question does that, and then we're going to encounter more of this in Chapter 3, so this really is a segue into what's happening in Chapter 3 that we hit on just a touch of before we get out of Chapter 2. So when we talked about finding a tangent line that was horizontal, we did that back with Raleigh's theorem, and Raleigh's theorem over here talked about the tangent line being horizontal on this side, and it talked about it right there. It said that we had a derivative value that was 0, right? So if we were looking for the horizontal tangent or slope of 0, it was equivalent to looking for a derivative of 0. Do you guys remember that? So if we were talking about a function being increasing, decreasing, or neither, we're talking about what happens to the slopes of that function. Because we've talked about the idea that if a function was increasing, what does it mean in terms of the derivative? When a function is increasing, what's the derivative doing? Right, the derivative is positive. Right? Imagine drawing those tangent lines. If the graph is increasing, what does the tangent line look like? Well, it looks like a line with a positive slope. And when a graph is decreasing, what does the tangent line look like? When the graph is decreasing, if it's going downhill, right, like a hill, what does a tangent line look like? A negative sloped graph, right? It's the slope is negative, so the derivative is negative. I'll draw a picture to sort of match this. And what would neither mean? It's not increasing and it's not decreasing. What does neither mean?
It's just constant.
It's constant. And constant is equivalent to having a derivative that's what? Do you know? Yeah, the derivative actually equals 0. So in other words, if we had a picture, I'll just draw a real simple picture. If I had a picture like so, right here, roughly, is where the derivative is 0, right? Over here, the derivative is positive, while the graph is increasing. And over here, the derivative is negative because the graph is decreasing. And right up here at the top, we're talking about the derivative being equal to 0. Okay, so you've got a picture of this going on in your mind, right? This graph is not a graph of the function at all. It's just a picture of the descriptions we're talking about. All right, so if we're wanting to know where the graph is increasing or decreasing, it's equivalent to asking where the derivative is positive or negative. Does that make sense? Okay, increasing, decreasing graph means a derivative is positive or negative. So we can answer the question about where this is increasing or decreasing by answering the question about its derivative instead. Because it's much easier to determine on a derivative, or it's much easier to determine where a function is positive or negative, because those are actually numerical values, right? I can actually look at a number and say, oh, look, it's positive. Oh, look, it's negative. That's easier to assess. So the first thing we're going to do is we're going to take the derivative and take a look at what that would look like. So what is the derivative of x to the 4th plus 2x squared plus 1? After all the hard derivatives you've done, what's this one? 4x cubed plus 4x. Everybody good with that? And the 1 turns into 0. All right, so what I want to know is I want to know where this equation is positive or negative. Well, the easiest question, though, to ask is where is it 0? Okay, so because if it's not positive everywhere, it's not negative everywhere, then it's going to change somewhere. It's going to change between positive and negative. And if it changes between positive and negative, that means it had to equal 0. That was the intermediate value theorem, which we talked about last time. So what we'd really like to know is because it actually asked us increasing, decreasing, or neither, we'd like to know where this is set equal to 0. So how do I solve where this is equal to 0? Unfoil it. What's another word for unfoil? You guys remember? Factor out, yeah. So what does this have in common? What do the two pieces have that we can factor out? 4x. And if I factor out a 4x, what am I left with? X squared plus 1. Good. Then what do I do? Right, I set each part equal to 0. The first one happens when x is equal to 0. What happens on the second one when I try to solve this one? Yeah, when I square root, I get a negative value there, don't I? So what happens? Yeah, this is non-real. It would be an imaginary or a complex solution. In this case, it's strictly imaginary. But this is a non-real solution, and we're working in the real number system. So this does not give me any information that's usable for what we're working in. Okay? So I only have one location where the x value is actually equal to 0. It's at x equals 0. All right, so let's imagine sort of doing a number line approach. We'll use another screen. All right, so my function was x to the 4th plus 2x squared plus 1, and the derivative that we had for that was 4x cubed plus 4x. And we found out that this is equal, that is, the derivative is equal to 0 when x is equal to 0. Okay, so everybody good with where we were? I think I got it all rewritten, okay. What we want to do is we want to know what happens over here on the left and what happens over here on the right to the derivative, because this is all based on the derivative being positive or negative. So how in the world could I figure out what happens to the left of 0? Plug in something to the left of 0, right? Negative. How can I make it bigger? Is that okay with you? All right, sure. Any value that is to the left of 0, so maybe we try -1. Or you could do -7. It really doesn't matter. You could make it complicated, but why? Right, so pick something that's nice and easy to work with. Choose a number on the left-hand side of 0. So -1 would work. What we're wanting to know is what happens in the derivative function at that value. So if I take the value -1 and I plug it into the derivative, that would be 4 times -1 cubed plus 4 times -1. What do I get? -8. What part of that's important? The negative or the 8? The negative is what's important. Because remember, my goal was to figure out what happened to the function before or afterwards in terms of being positive or negative. So it is negative on the left-hand side of 0. And then we'll try a point over here on the right-hand side of 0. What's the nicest point to try? 1. I like 1s. 0s are also really nice to try if it's a value that's in that interval. Our actual value, 0, doesn't work because it's the place where we're splitting our graph. But all right, so when I plug in the number 1, what do I get? What do you get? We get +8, yeah. Thought I heard something different. And the point, again, the important part anyway, is the fact that it's positive. Right? So let's sort of just write this down. You don't have to write down what I'm going to write down, but I want you to realize what we just found. We found that the derivative is negative from -infinity to 0, and it's positive from 0 to infinity. That's what this sign chart, and that's what this is called. It's called a sign chart. That's what that sign chart tells us. But what did the question ask? It asked about the function f of x, right? It didn't ask anything about a derivative. We just used the derivative to answer the question. Or we are in the middle of using the derivative to answer the question. So we actually have found out that the derivative is negative from -infinity to 0. So when the derivative is negative, what does that tell us about the function? It's decreasing. A derivative being negative tells you that the function is decreasing. Remember, derivatives are just slopes of tangent lines. So if the slope of the tangent line is negative, then the graph was going downhill. It was a decreasing graph. So our function f of x is decreasing from -infinity to 0. It's going downhill. And it is increasing for the same reason from 0 to infinity. That's what this information tells us. Now graph it. Take a look. Does the statement we just made match what your calculator is going to tell you? So if you take a calculator and you graph x to the fourth plus 2x squared plus 1, what does it look like? So what we're doing now is basically a check step. It does not verify the information we just did algebraically. It just verifies it graphically, which is a good thing to do, but it isn't the right way to answer the question, okay? We're trying to show the interrelationship between derivatives and function values. What's it look like, more or less? Did you get a graph?
Yeah.
What does it look like?
It looks like
It looks like
a parabola.
a parabola. It's not because it's x to the fourth, right? But it looks like one. Where does it cross the y-axis? Above or below the x-axis?
Above.
Above. So does it look something like this, Austin?
Yeah.
Yeah. The graph looks something like that. It actually crosses at x equal 1, and that's because of this plus 1 here at the end. But this is the basic graph.
Would you want us to graph that?
You don't have to. I mean, but if you wanted to, it would be okay, but I wouldn't expect you to. Is it decreasing from negative infinity to 0 along the x-axis? Yeah, it is. Is it increasing from 0 and up? Yeah, it is. And so this graph verifies the statement that I wrote at the end. It makes it all seem reasonable. And that's what the graph does. The graph doesn't tell you an answer, but it gives you whether or not your answer is reasonable. We're good to go? All right.